All right, welcome everyone to the first lecture of CS 188 for the spring semester. Let's start with a couple of announcements, clarify some things about the logistics of the class. The website for the class lives at berkeley.edx.org. So we're using the EDX system for the class. And at berkeley.edx.org, if you don't have an EDX account yet, you should sign up for an EDX account. And then on there, register for CS 188 spring semester. For discussion, we will use Piazza. Whenever we feel like we need to blast an announcement to the class, we will post an announcement to Piazza and overrule your email settings and make sure it goes out to you. So make sure you signed up there, because that will be the way we blast things out. You already have something that will be going out tonight, and that's due on Friday. This is the Project Zero. It's meant to get you familiar with Python if you aren't yet. Get you familiar with the instructional machines if you want to use them. You can also use your own machine, whatever you prefer, but it's to get you used to whatever setup you'll be using throughout the semester for the projects. So that's due Friday at 5 p.m. This will go out tonight. There will be one-time optional lab office hours listed on the slide there. They're meant to help you get going on P0. A lot of you will just kind of look at P0, be done in an hour or two, and that's it. But if you haven't worked with Python before, haven't worked in Unix before, and so forth, it might be useful to come to the lab hours, bring along your laptop, or use the instructional machines right there, and GSIs will be there to help you. If you want an account form, you can come and get them after class. What are these? They allow you to log into the instructional machines. You don't need them for the class, but if you want to use the instructional machines to do your projects, then you'll need an account form to be able to log into the instructional machines. There's also a math self-diagnostic. This is actually optional. The reason we do this is because the class is very bipolar in the sense that the first half of the class is very computer science-y. It's what you're mostly used to. It's algorithms, programming. You'll jump right in and be happy. Then right in the middle, we switch to a very mathy part of artificial intelligence. It's the way a lot of AI is done these days. We're not going to avoid that. But the problem is that a lot of people don't realize this is coming. And then by the time it comes, it's too late to drop out. OK? So do the math self-diagnostic to check that you're prepared to do the math that only comes in the second half. Sections will start next week only. Some people have emailed me, I can't register for section, or I was registered for section and I'm not anymore now. No problem. You don't have to register for section. You can go to whatever section you like to go to. We will report how many people showed up in each section, so that if you're the kind of person who likes a really crowded section, next week you can go to the crowded section and the other way around. If you are waitlisted, unlike probably many classes, it's very likely you're going to get in. The reason being that we arranged a switch of classrooms when we saw there were too many students for the original classroom, which could only take 200 students. We saw there were 300, and now there is 360, but this classroom can take up to 400. University regulations don't allow you to take more students than a classroom can fit, but so up to 400 can fit. So if you're waitlisted and there's still less than 400 people in the class, it's likely you're going to get in. Very likely. Office hours start next week. If anything comes up in the meantime, you can contact us through Piazza, through the staff mailing list, which I'll show in a couple minutes. And you can come find me after lecture or find the GSIs in the lab hours. OK, so this is artificial intelligence. This is our introduction lecture. This is the course staff. So let me do a couple of quick introductions. I'm Pieter Abbeel, professor teaching the class. We have 5 GSIs. And let's see. 4 of them are here, it seems. So let's start with Judy. Maybe you can stand up and wave at everybody. This is Judy Hoffman. Judy is a PhD student working in computer vision, one of the main areas of artificial intelligence. Judy was also an undergrad here, so she'll understand your pains if any pains come up. Brad Miller, can you stand up for a second? So Brad is a PhD student in computer systems. We're super happy to have him on board. A, he's really excited about learning more about AI. B, he's really good at systems, and we're doing a lot of upgrades to the infrastructure that grades your projects. He's been working on that since the beginning of December, and it's coming together very nicely. Then James Ferguson. James is actually still an undergrad here, so he'll definitely understand all your concerns. James is a junior, took 188 last spring, totally aced it. One of the very few A+ in the class that semester. It will be great to have him. Then fourth one who's here is Nick Hay. Nick is a PhD student in actually Stuart Russell's group. Stuart Russell is the author of the optional textbook, in case you're wondering. So Nick works with Stuart. Nick has also been working since the beginning of December on the autograders for the projects. Then Jeff, unfortunately, can't be here right now. He has a Comcast guy coming by, and the Comcast guy is not super punctual. I think you all know what's going on there. But he'll try to be your next lecture so you can see who he is. All right, so course information. Announcements will always go on the webpage. If we think they're up for discussion, they'll definitely also go onto Piazza. If you have questions, the primary mode of channeling your questions is Piazza. If it's something that's more appropriate for the staff list, that's not really, you don't think the answer will be relevant to other students, just email us directly or ask a private question on Piazza. The course is very likely webcast in that don't count on it 100%. Sometimes something goes wrong, but most of the lectures should be up for you to watch at your leisure, at home, behind your computer. In terms of course technology, I mentioned the EDX website. This is something we did last semester. We switched from kind of more paper-driven assignments to everything electronic. And we're using EDX. It's actually something one of my PhD students helped develop last year and through the summer. It's not a finished product. So there are a lot of advantages to using EDX, but it's far from polished. So sometimes you'll see some rough edges. If they affect you, let us know. We'll see what we can do about it. But bear with us when there are some rough edges. Overall, I think it's a big improvement, and the surveys last semester also suggested students were very happy with it, despite some of the rough edges. So what are some of the great features? Your homeworks will all be electronic. What that means is homework goes out just like the math self-diagnostic already went out, and you'll have a set of questions online. You can discuss them with other students as much as you like. You have to submit your own. You submit into the answer box, numerical, multiple choice. Sometimes it's something related to graph structure or strings. If you get it wrong, it'll just tell you you got it wrong. You get another trial. You get to keep working until you get it right. The philosophy here is that we think homework is really for learning. You should be able to keep working till you fully get it. And often the questions, by the way, will be randomized. So it's not the case that, oh, I get it wrong, I'll just try again until I get the right one. The question might change on you, but it'll be on the same concept. So that's the philosophy behind the homework. Same for the projects. For the project, you'll be able to keep submitting your project, get feedback about how many points you would get for this particular submission, and you can keep submitting as many times as you like. Now, one of the tricky parts of the previous semesters has been that you submitted your code, and you would get feedback, and it would say, you have this many points, and this question was wrong, and so forth, and you're like, I thought I got everything right. It ran on my machine. This autograder is doing something weird, and I don't know what it's doing, and now I'm losing points, and I'm stuck. So that's what Brad and Nick have been working on since December. The big change this semester in the projects is going to be that you get our autograder. So when we release a project, you get the autograder code. You'll be able to type on your command line the autograder command. It'll print out a report for you. And you can also look at the autograder code and see what it's testing, see what test cases it's using, see what the input is for the test cases, see what the supposed output is, and it'll report when your output doesn't match. So you'll get the full insight into what's going on. This should help you in debugging your code compared to having these black box feedback. Another feature is that often right before the deadlines, autograders would slow down tremendously because everybody is submitting. Now, the advantage of this new system is that because we run the same code you run, if you want to debug your code, you can do it all on your own machine and be sure that you get the right points based on what you do on your own machine. Of course, you don't get grades based on running on your own machine. You still have to submit. But you can submit maybe once or twice to verify that things are indeed right in our system, and you're done, as opposed to banging the autograder right before the deadline with many, many submissions. On that point, if right before the deadline you decide to submit, that's fine. If the autograder only gets back to you an hour after the deadline because it was busy, you get your grade, as long as your submission is in on time. All right, but keep in mind, despite these things that we're doing that we think are great to allow you to keep working on things until you get it, and you can come to office hours if you're stuck on something, there are some rough edges, so help us fix them. If you see something that's not good, maybe we can work around it. Let us know. Prerequisites. Something that's a little different this semester because we expanded the size of the room and everybody can get in, is that you're not getting in based on exactly how closely you satisfy the prereqs. You're just getting in. This also means it's kind of up on you to evaluate whether you are ready for this class. As I said, for the math, there's the math self-diagnostic. For programming, Project Zero is not really the test to see if you're ready for the programming in this class. Project Zero is just to get you familiar with Python, Unix if you're going to use that, and the auto-grading system. Project One is the real test to see if you're ready for this class. Project One will go out next week, Tuesday. It'll be very soon that you can verify that. But that burden is on you. You have to check with the math self-diagnostic and Project One whether you're really ready or not. What we recommend is 61A, 61B, and CS70. The work ahead of you is 5 programming projects, not counting Project Zero. You get to work in groups on the programming projects, groups of at most 2. So you might want to figure that out today, who you might want to work with. You get 5 late days over the semester. So if something comes up, you can use those late days at your kind of convenience whenever it's best for you. A maximum of 2 per project. After 2 late days, the autograders will shut off. So your budget is 2 per project, but 5 over the semester. There are 2 midterms and 1 final. One of the reasons we started doing 2 midterms is because you get to work till you fully learn the material on the homeworks and the projects. Some students end up underestimating, or maybe the other way around, they end up overestimating how well they learn the materials because they aced every homework and every project because the system is set up that way. They have a good chance of doing that if you're really motivated. But the midterms and the exams are under time pressure compared to the homework. You don't get to submit as many times as you like. It's 1 submission at the end of the midterm, right? So it's a little different scenario. So we have 2 midterms as opposed to what used to be 1. So after the first midterm, you get an additional evaluation of where things are at. We'll also give you a practice midterm a week before the first midterm, so you get a good feel for what the midterm questions are going to be like. Participation can help on the margins. This is participation on Piazza, participation in class, any kind of participation that makes the class better. You're not going to get a certain amount of points for it, but if you're right at the boundary between 2 letter grades, and we know you because you were the person always being so helpful on Piazza, whatever, we'll bump you to the better letter grade of the 2. It's on a fixed scale. So on the website, you can see, depending on where you land, what your letter grade will be. In terms of academic integrity policy, you can read it on the website. Essentially, it's a very harsh policy. If you cheat and we catch you, then we report you, and campus will deal with you. We'll have fun contests. So you're working on the projects, and you say, this is not enough for me. At the end of the projects, there will be open-ended contests. What that means is there will be some open-ended thing where you can do as well as possible. And the more clever you are, the better you'll be able to do. Don't spend entire weeks on this, right? It's just a couple of points of extra credit, but spending a few hours on this to learn more can be a really good thing. Textbook. This is new in the sense that what's new is that I don't strongly recommend the textbook anymore. Surveys have shown that some students benefit from the textbook, some don't. Many of them just think it's too expensive to even consider to use it, or just run out of time looking at it. There is a textbook. There is one AI textbook that's kind of the standard book. That's the reference for almost all AI classes shown there. It's by Stuart Russell from Berkeley and Pieter Norvig from Google. It's a good book, but it doesn't exactly follow how we do things in this class. So what's in there is great, but sometimes the way things are explained are different. And if you go in with a little bit of confusion about lecture, trying to get it clarified in the book, you might get more confusion because it's a different explanation. So keep that in mind, how you use the book. It's good to learn more. It's good if you understand what's in lecture to go read more. It's not that great if you don't understand what was in lecture to then try to understand it. OK, what about any logistical questions before we start with a little more technical topics? Yes? Are you trying it out? Let's check. It's just a show answer. That means the deadline is set wrong. OK, this is a great feature. It's a self-diagnostic, so it's not the worst place for it to happen. But what happens is after a homework is due, James, maybe you can update it. After homework is due, what happens is you get a show answer button. If you click on the show answer button, what you get is an explanation of A, what the answer is, and B, why it is the answer. Until the deadline, normally the show answer button wouldn't show up. There's still some quirks with the infrastructure, so this time it did show up, but we'll fix that. Thanks for pointing that out. Yes? Discussions are not being assigned. You can go to whichever discussion you want to go to, whatever time is best for you. Probably some will be a little overcrowded because it's everybody's favorite time slot. And then it'll sort itself out based on people who prefer not to be in an overcrowded section deciding to go to a different one. But we'll report back on how crowded sections are so you have an idea of which time slots you could go to if you want a quieter section. Yes? Okay, are there penalties for late project submission? These late days are completely free. So you have a budget of 5 late days. You can use them at whatever way you like to use them. But that's your hard limit. So, and it's 2 at most per project. But no penalty for using 2 late days. It's fine. It's also automatic. Don't have to say anything. The system will know that you were a day late. Put that in your budget as you used 1 late day. Yes? 140 or something. Let's see. No, it's not a number of hours. It's a number of days. So when you use 5 minutes, you use the day. We're rounding up to the nearest day. So 5 minutes is a bad use of your late day. Yeah. Yes? Say that again? Likely, yes. But you'll find out quickly, I think, when you're working on project 1 and working through the self-diagnostic, and you can look at CS70 and see if we're stuck, whether you'll have covered the right materials by the time we're halfway through the semester or not. Okay. Yes? No, you want more exams? There are 3 practice exams that go out the week before the exams. Those are optional. But yeah, that's the 3 exams. Yes? We have them tentatively set. If you look at the syllabus, you see an entire schedule of when every homework will go out, when it will be due, when every project goes out, when it is due, when the midterm is. For the midterm, I'd like to see if we can find a room or 2 rooms such that you have more space. You're not packed together this much. So that might affect, for the midterms, the exact time of the day, or even shuffle the day back or forwards by a day. We hope to find out soon. Any other questions? All right, then let's talk about what the class is about. What is artificial intelligence? What can it do for us, in general for other people maybe? And what is this course? So let's start with the science fiction story. Let's look at what Hollywood has made for us. Who knows these guys? Okay, in gold we have C3PO. What does C3PO do? Essentially Google Translate, right? Now, how about the other one? Who's that? R2-D2. What does he do? Not a whole lot of sensical stuff. How about this guy? It's our former governor, right? So Terminator. So what you see here on the left is earlier robots where Hollywood was kind of positive about what AI might bring us, but it kind of turned dark on us pretty quickly, at least what Hollywood is thinking about it. This is a person/robot who came back from the future to kill people now. Later, in the 90s, what started happening is that Hollywood started realizing it's not just the robots that can affect us, even software can be dangerous to us. And a lot of sci-fi was then focused on software. Then they start realizing that maybe the robots might be indistinguishable from us. Or they might stay looking very quirky and very different from us. But overall, it's a very dark picture. There are some exceptions out there, like, let's say, WALL-E was kind of a nice robot, good vision of the future for the robot, maybe not for the people. But overall, it's a pretty dark vision of what might happen if AI really succeeds. Am I worried about that? At this point, definitely not. And by the end of this class, you'll realize you definitely don't have to worry about these things yet. So what is AI? What is it that we really try to do rather than making movies? Well, there's a couple of different ways of looking at AI. First one is that AI means try to make a system that thinks like people. Okay, so you can imagine that you study the brain, you try to see what's going on in the brain, and then try to build something that thinks very similarly. It's actually still happening. A lot of people are working on this in cognitive science and neuroscience. Very difficult subject. It's not really where AI is headed right now, because we still have a very poor understanding of how that all works. Another thing you could say is, well, it doesn't matter how the machine thinks, as long as it acts like us, we'll be happy with it. This is actually a very old school of thought. This goes back to Turing. And in the early days of AI, essentially he said, well, maybe one way to verify whether something is a real AI or not is to check whether it can act like us. And the specific format he put forward was a Turing test. And the idea here is essentially a chat bot. The idea is that you connect to a chat agent. On the other side, there could be a person or there could be a computer. You don't know. You start chatting, and the question is, can you find out whether on the other side there is a person or a computer? If you can, then that computer didn't achieve to act like people. If you can't, then you pass the Turing test. You build a computer that acts like people. So people started doing this. And some people got hooked on these computer bots and could chat with them for a long time. But from a kind of scientific point of view, there was a big issue there. And the big issue was that the focus ended up not being, after a while, on building something intelligent, but rather on modeling all the quirky things people do and all the things people are not necessarily that great at. Let's say you ask the chat bot, what's the square root of 1059? If it answers right away, because it's a computer and it knows, then you know as a person, another person probably couldn't do this, very unlikely. As you're crippling, to pass this test, you're crippling the AI to make it more like a person. And on the other hand, you start doing things like, oh, what's really important to build an AI is to have a favorite movie or a favorite Shakespeare play and so forth. Those are not really the problems we're after. That's not the kind of things that will help us build an AI that can do something useful for us. it's really going on a sidetrack to pass these tests. So another approach is to say, well, what we really should be doing is look at the thought process. It doesn't have to be a brain that's wired up, but somehow the thought process has to be rational, the way we believe people do their thinking. And this goes back all the way to Aristotle in the Greek times. Unfortunately, there has not been a whole lot of progress on this. Now, where the most progress has happened, and what this class is mostly looking at, is to act rationally. What's the idea there? The idea is that you have some type of behavior called rational behavior, which we'll unpack over the next couple of slides. And if you achieve that type of behavior, then you're building a good AI. If you don't, then you still have a ways to go. So what does it mean to be rational? In this context, it's not rational as opposed to, let's say, quickly getting mad when somebody annoys you. It is rational in a very mathematical sense. It means that you define some goals. Those are the goals you'd like to achieve or you'd like your robot to achieve. And acting rationally then means that you do the optimal things towards achieving those goals. Mathematically, how this will be formalized in this class is by maximizing your expected utility. And we'll look at this in a little more detail, but really maximizing your expected utility is what this class is about. And so it's, while you think it's artificial intelligence, really it's about computational rationality, getting computation to act rationally for you. So what is this maximize your expected utility? A lot of what we'll do in this class is looking at maximizing. How do you maximize some criterion? That criterion will then be utility criterion. We'll look at what is the right thing to use as your utility criterion such that you're doing something meaningful when you're maximizing your utility. Then we'll see that often in the real world, and we're trying to get these systems to act in the real world, things don't happen deterministically. There is a lot of randomness in the processes. So you can't just maximize for a certain utility, a certain outcome, because there'll be some stochasticity. So rather than maximizing for a particular outcome, you try to maximize, get your behavior set on average, you maximize your payoff in terms of utility. So we'll look at methods that can handle the right kind of averaging over different outcomes, where outcomes, the goodness of outcomes is measured by this number that we call utility. OK. So what about the brain? You might think, yes, it's all good to build an artificial intelligence, but we already have human intelligence. And as far as we're concerned, at least most people in AI, human intelligence is still quite superior to artificial intelligence. So can't we use some information from how the brain works to get AI to work better? Or can we maybe build an artificial brain, just build the same structure, maybe in transistors rather than neurons, and see if we can get the same behavior out? Turns out that the brain is still very poorly understood. But people have poked at it and tried to get an understanding of what might be going on and so forth. And if you look at what's happened is there's some understanding of how the brain works. This has inspired some AI algorithms that we'll look at, but often the way to make progress is to not try to stick too closely to how the brain does things. Let's say if we look back at how progress was made in getting humans to fly, right? People were trying to build essentially birds, looking at nature, build flapping wing kind of systems, and see if they could fly. And they didn't succeed. It's once they said, let's not worry about doing it like nature. And they said, let's just build fixed wings that don't move and build an engine such that with the air velocity over it, we'll get the lift, that they really start succeeding at getting aircraft up in the air. So often it's a departure from how nature does things that has given us success in engineering. And the same is true for artificial intelligence. So we're not going to be all that close, but there will be some inspiration coming from the brain at some times. So the saying that a lot of people use to kind of emphasize this is that brains are to intelligence as wings are to flight. Now, there are two key lessons from the brain that will come back in the structure of this class. And that is the way we get to act rationally or intelligently can be split into two lines of reasoning. One line of reasoning is the one that's memory-based. You have seen things before. And because you've seen it before, and you've seen that a certain action led to a good outcome, you use your memory to then decide what to do in this new situation that is quite similar. That's machine learning. That's what machine learning will do for us. Another line of approaches says you actually don't need to have seen how things play out to then copy what was done in similar situations. You can simulate in a computer or in your brain, if you were to take certain actions, what would that lead to? And you can simulate different sequences of actions and then see which sequence of actions leads to the best outcome, or on the average, if it's a stochastic system, leads to the best outcome, and then go with that sequence of actions. That's a simulation-based approach. That'll be our first half of 188. The machine learning will be the second half. All right, so before we dive into how things are done today, let's take a look at history and how AI came about, right? Back in the early 50s, people started building computers. And at that point, initially they thought of them as just fancy calculators, but at some point they started realizing computers aren't just useful for calculation. You can do other things with computers, right? You can move data around. You might be able to reason about certain things in the world, maybe about a chess game or about a checkers game and so forth. And so in the early 50s, people started thinking, well, maybe we can build some kind of AI based on these computers. And really what they were doing at the time, in some sense, was dreaming about what AI would be like if they had computers that are still far in the future from where we are now, but they then have computers that are less powerful than what you could put in a cell phone 5 years ago, right? So they essentially had no computational power, but they were dreaming of these things that might be possible if they had a lot of computational power, and actually they didn't really realize how much computational power would be needed. Let's watch a video back illustrating what some of the thought leaders of the time were thinking about where AI was headed. To put this in a little bit of context, these are famous people. You'll recognize some of these names. And they're making pretty bold predictions about what AI will do in the very near future back in the 50s. Also, a little more context is this is the Cold War era, so people care a lot about translation in that period. They want to translate everything the Russians do into English automatically to see what they're inventing and to keep up with them, right? Oh, that's not good. Try this again.
The Thinking Machine.
Hello again. With me tonight is Professor Jerome B. Wiesner, Director of the Research Laboratory of Electronics at MIT. Dr. Wiesner, what really worries me today is what's going to happen to us if the machines can think. And what interests me specifically is can they? Well, it's a very hard question to answer. If you'd asked me that question a few years ago, I said it was very far-fetched. Today, I just have to admit I don't really know. I suspect if you come back in 4 or 5 years, they'll say, sure, they really do think. Well, if you're confused about how you think I feel.
We're just really beginning to understand the capabilities of the computers. I've got some film to illustrate this point, which I think will amaze you.
That man is playing checkers against the computer, is he?
Sure, it plays pretty well.
Now, which color?
While most computer scientists saw it as a mere number cruncher, a small group thought that the digital computer had a much grander destiny. Being a general-purpose machine, it could be programmed to do things which in humans require intelligence. Play games like checkers and chess, and solve brain teasers.
Let's see what
The field became known as artificial intelligence.
Can machines really think? Even the scientists argue that one.
I'm convinced that machines can and will think. I don't mean machines will behave like men. I don't think for a very long time we're going to have a difficult problem distinguishing man from a robot. And I don't think my daughter will ever marry a computer. But I think the computers will be doing the things that men do when we say they're thinking. I'm convinced that machines can and will think in our lifetime.
I possibly expect that within a matter of 10 or 15 years, something will emerge from the laboratory which is not too far from the robot of science fiction fame.
They hadn't reckoned with ambiguity when they set out to use computers to translate languages.
A $500,000 supercalculator, most versatile electronic brain known, translates Russian into English. Instead of mathematical wizardry, a sentence in Russian is to be fed.
One of the first non-numerical applications of computers, it was hyped as the solution to the Cold War obsession of keeping tabs on what the Russians were doing. Claims were made that the computer would replace most human translators.
Now, this is, of course, you're just in the experimental stage. When you go into full-scale production, what will the capacity be? We should be able to do about, with a commercial computer, about 1 to 2 million words an hour. And this is quite an adequate speed to cope with the whole output of the Soviet Union in just a few hours computer time a week.
When do you hope to be able to achieve the speed?
If our experiments go well, then perhaps within 5 years or so.
And finally, Mr. McDaniel, does this mean the end of human translators?
So yes for translators of scientific and technical material, but as regards poetry and novels, no, I don't think we'll ever replace the translators of that type of material.
Mrs. McDaniel, thank you very much.
All right, so that's how people were thinking about AI back in the 50s. So 50s, there was actually some reason for optimism at the time. People made some progress on things that they hadn't thought would be feasible before to be done automatically. They had a circuit model for the brain. They had Turing's paper on how computers could maybe do something else than just number crunching. And then there were some early programs that were written to play checkers, some very simple chess play, even geometry proofs. There was logical reasoning systems. So there was a lot of systems that came in place and that seemed very promising. Now, the 70s and through the 90s, what people thought is all we need to do now is just code all our knowledge about the world into these logical systems, so all the facts of the world are coded into the computer, and then the computer can do the reasoning for us about what we should be doing in the world and so forth. Unfortunately, it didn't really work out. There's a couple of reasons for that, but at the end of the day, that optimism wasn't really right. They said in 5, 10 years we're going to have this. In fact, after even 40 years, they didn't have computers proving very complicated theorems and so forth. It took a really, really long time. In fact, at that point, there was an AI winter where people said, you've been promising us 40 years ago, you're going to do things in 5 years, then 10 years, then 15, and 20. It's never happened. We're done with giving money to people who work on AI and think that they're going to make something happen. Then, in the early 90s, what started happening is the people that still thought AI was a good thing to work on started looking at more probability-based systems, account for uncertainty in a probabilistic way. And this really opened up new avenues to model the kind of things that we care about in the real world, where very few things are deterministic. And from there, people start building up machine learning algorithms, probabilistic reasoning systems, and so forth that really are now at the core of many systems that we see out there deployed. Think of things like web search, machine translation we have now, and so forth. And we'll see many examples in the remainder of the lecture that have these more probabilistic, optimization-based techniques behind them. So we started seeing something a little bit more of an AI spring by the end of the 90s. So let's take a look at what might be possible right now. Little quiz for you guys. Can AI play a decent game of table tennis? Who says yes, raises their hands. You're all right. AI can play a pretty decent game of table tennis. Can AI play a decent game of Jeopardy? Yes, it recently did so and was very convincing. Can it drive safely along a curving mountain road? Yes, this also happened not too long ago. Can it drive safely along Telegraph Avenue? A lot fewer hands going up. It's a little more debatable. It's hard for humans to drive safely along Telegraph Avenue. So maybe a question mark there. Buy a week's worth of groceries on the web. Sure, yeah, why not? It's just submitting some kind of message into a system, right? Should be able to do that. How about buying a week's worth of groceries at Berkeley Bowl? Well, that's a lot trickier. Now you have to navigate among people. That's not yet working. How about discover and prove a new mathematical theorem? Who thinks yes? This is kind of a subtle one. There's two things in there. It says discover and prove. So the proving part, actually yes, AI has proved theorems that were hypotheses before in pretty clean ways that were surprising to people. But discovery is a whole other thing, because there's so many things you can prove in mathematics. And most of the things you might be able to prove are just not interesting. Like maybe you start from a number system and then you say, oh, actually 12 plus 3 is 15. That's a new thing I proved today. And nobody's interested. So there's a really subjective thing there in terms of what makes for an interesting theorem to prove. And that's really hard to figure out. How about converse successfully with another person for an hour? Might depend on the person, but I would say no, unless, it's just a few people out there. Perform a surgical operation. Who thinks yes? Some people say yes. Okay. You raise your hand. Are you ready to go in for surgery? Like, you want an AI or a surgeon? Yeah, so there are some eye operations where a surgeon will examine what needs to happen, put some settings on the robot, and the robot will very precisely execute whatever the surgeon asked for. So it augments the surgeon and allows to do surgery at a much higher precision than a surgeon could. It's not going to make all the decisions, but it's going to execute very precisely, right? There are systems where surgeons teleoperate robots where they make motions with one robot, another robot that's much smaller is inside the patient and makes smaller motions that mimic the surgeon's motions. There's a lot of robotics going on in surgery. But are we ready to just kind of walk in and a robot take out our kidney and put it into somebody else? Probably not. So it's kind of at the boundary. Maybe in a few years if you're back here. Put away the dishes and fold laundry. Okay, we'll say yes. It's a bit limited, but we're doing it at Berkeley and we're proud of what we're doing, and you'll see a video later. Translate spoken Chinese into spoken English in real time. Who says yes? About a third of you. Maybe because it's a subtle one. It could definitely do it in real time. It might not be able to do it very precisely. So we'll click this for now. You might probably get more out of it than the Chinese if you don't speak Chinese, but it's not perfect yet. The speech recognition part works really well, by the way. Write an intentionally funny story. So it's a very subtle way of using language, right? Not ready for that. Let's take a break here. And after the break, let's look at what unintentional funny stories AI has been able to come up with. All right, let's restart. Any questions about the first half of lecture? Okay, let's continue then. Unintentionally funny stories. Here's your first one. One day, Joe Bear was hungry. He asked his friend Irving Bird where some honey was. Irving told him there was a beehive in the oak tree. Joe walked to the oak tree. He ate the beehive. The end. Okay, so this is a pretty good story to come up with for this AI system. It's actually pretty close. It's really close. And that's what makes it funny. It's just a slight mistake at the end, not realizing that you don't eat the entire beehive. You got to reach in there. That's the slight mistake, and that's what makes it funny. Okay, while we'll look at this cartoon, I want to bring to your attention another person who's contributing to this class. She's not officially on the staff. She started working with us last semester. This is Katrina Yim. She was a Berkeley student, graduated a few years ago. What she would do is if she were in a class, she would show up 10 minutes early to lecture, and she would draw the most amazing cartoons about the materials you covered in the previous lecture onto the board. So last semester, Dan and I were teaching 188 together, and we brainstormed about what are the things we really could do to make things even more fun than they already were. And one of the things we can always say, hey, why don't we get in touch with Katrina, hire her kind of through a separate channel, and work with her to illustrate our slides. So all of these drawings you see on the slides were made by Katrina. And you'll notice that they're actually usually very topical, and often students will find that they summarize the concepts pretty well and are good mnemonics for what's going on. Not that this story is the most important story to remember. But remember Katrina. Henry Squirrel was thirsty. He walked over to the riverbank where his good friend Bill Bird was sitting. Henry slipped and fell in the river. Gravity drowned. The end. So what's going on here? Again, the first few sentences, pretty good. Coming out with a pretty nice story. And then gravity drowned. What's happening there? Think of it from a computer point of view. It's generating sentences, and it has a subject, it has a verb, that part's working out. It's just not realizing that for this kind of sentence, it's not the cause of the drowning that matters, but it's who's drowning that you want to be talking about. Last one. Once upon a time, there was a dishonest fox and a vain crow. One day, the crow was sitting in his tree, holding a piece of cheese in his mouth. He noticed that he was holding the piece of cheese. He became hungry and swallowed the cheese. The fox walked over to the crow. The end. Okay. What's the problem here? Physically, nothing's wrong. This actually could happen, right? If it were to, it's just not the way you would tell a story. You're not conveying the information people would convey. You're conveying kind of a random set of facts. Are we doing better now? Let's ask Siri. Tell me a story. Once upon a time? No, it's too silly. That's where it stops. So, not too much further along yet. Let's look at another natural language demo. And what we'll look at here is automatic transcription. So, captioning system for TV. The thing I want you to pay attention to is the mistakes the system makes. The system is not perfect, and try to see what the mistakes are and think about kind of what's going on there.
Friends, family, and classmates said their final goodbyes yesterday at her funeral in East Falls. Now, Asia Adams was buried today, and on this day, a major break in the case. Police sources tell NBC 10 that a person is in custody and appears to be a strong suspect. They will have more information in the morning. Reporting live from police headquarters, I'm Denise Nakano, NBC 10 News.
Good evening. And also, new at 11 tonight, a Pennsylvania state trooper injured in a car crash. Chopper 10 over the scene, the eastbound lanes of the PA Turnpike in Upper Moreland Township. The officer was taken to Abington Memorial Hospital. The trooper's injuries are not life-threatening, we're told. 2 lanes of the turnpike.
Okay, so this was actually pretty good. If you just were able to read, not listen to this, you'd probably know what's going on. But there were a couple of errors. One of the errors that stands out is in the very beginning. It says the class must say their final goodbyes. Sounds like goodbye, but it was transcribed as goodbye as you write best by, right? Sounds the same, so the computer heard things right, was able to transcribe it into something that would sound the same if you read it aloud again, but it just doesn't have the right meaning when you see it spelled out. So there's some disambiguation that needs to happen about the meaning of the words that I wasn't able to do here. But it's pretty close and definitely a useful system as it currently is. The other way around turns out to be a little easier to get right, even though systems might sound a little robotic from text to speech. Let's look at other language processing technologies. Watson is kind of the big example from the last couple of years. That's really language processing. It's really, it's phrasing questions, but really it's answering questions, right? It's answering a question, it's pulling in all the knowledge from the internet into its own computer, then analyzing what's there and somehow coming up with an answer to pretty complicated questions, at least for humans. Machine translation. You go to a web page, Google can translate it for you. Translations aren't perfect, but they're often good enough that you can get a good feel for what is going on in that text. Language processing is also used for web search in general, for text classification, spam filtering, and so forth. So a lot of applications of artificial intelligence in language processing. Vision is not a main application area. It's the area Judy and Jeff work in. So one of the applications you might have already seen is things like face detection in cameras. It knows where there is a face. It knows to focus on them. It might even detect when somebody's smiling. Object detection, we'll see in a minute a demo. Segmentation of scenes into different parts. Classification of what's in an image. All of these are tasks that people are making pretty good progress on. So let's look at a demo of actually our governor again. Where is he? Kind of what computer vision is after, right? You get this stream of images coming in, and you extract all the relevant information out of them. Okay, let's stop here. It's going to get a little wild. You can watch the remainder at home. Now let's look at another demo of an actual computer vision system, not a Hollywood system. That was Terminator 2, by the way, if you want to watch it at home. Same thing here. Frog, fox, Dalmatian, bulldog, fox, frog, Terminator frog, something like that, right? That's how the Terminator would work. The computer vision is pretty much there, at least for these kind of creatures. So it's still an open problem to recognize everything that's in an image, but there is some good progress there, and this is really AI techniques that are underneath what's happening in these computer vision systems. One big thing in artificial intelligence is that we're not necessarily limited to the same sensors as humans are using. With things like the Kinect laser rangefinders, you can often get different kind of readings, let's say direct distance readings rather than just a RGB image. And that can give you additional information that humans wouldn't have, but you might as well use if you're doing computer vision. Robotics, that's kind of the maybe mostly originally envisioned application of AI. What can we do there? Let's look at some examples. One of the applications that a lot of people do research on is making robots play soccer. Let's look at how far along we are there. Now, one of the things you might find is that when you start using learning techniques to make these robots learn how to play soccer, they could come up with some pretty unexpected behaviors that you might not have programmed in yourself. What else do we have in robotics? One of the big things that is about to happen is getting autonomous cars, right? One of the biggest impact things in robotics, I think, in the consumer market in the next 5 to 10 years. So imagine your commute comes just leisurely doing something else, right? No more accidents, presumably. No more looking for parking. So a lot of benefits for autonomous cars. So let's take a look at where things are at right now. This is a video of the Google car. Which actually took a ride in last Friday, but this is not my video. This is a video they published a while ago. So this is an autonomous car. This is San Francisco, as you probably recognize. Pretty complicated negotiation of metering. It's a little dark. So they have detection of pretty much anything that's going on the road. They know how to recognize that and act upon it and drive safely, right? They've done hundreds of thousands of miles by now. In fact, they did it before anybody knew they were doing it, and then all of a sudden it leaked. But they're doing really well. They don't do it the way humans do it, right? Google actually catalogs the roads ahead of time. So these cars don't drive on new roads they haven't seen before, at least as far as the public knowledge of this is concerned. They drive on roads where Google cars have been before, precisely mapped out what the road looks like, and then when the autonomous car comes around and on this scene, it knows what it should look like and knows, based on the images seen in the past, the new images, where it should be positioned, right? So it's a little different than human driving, but it's very capable. Let's look at something we did here at Berkeley. This is a robotic laundry system. You should come check it out in my lab if you want at some point. Just let me know. We do demos on a regular basis. So this is sped up 200 times. You don't want to watch this in real time. So this is something we did about 3 years ago now. By now, the actual robot actually has managed to speed up about 100 times, but it's not as cute a video as the one that we made here. So this actually succeeded at folding arbitrarily towels put in front of the robot, 50 towels in a row. At that point, which took the student 50 times, 30 minutes of sitting there, the student was exhausted. And we said 50 out of 50 is enough to claim that we can do this. Now, one of the robots that's one of the most exciting ones coming out of Boston Dynamics, and actually what's happening right now is DARPA, which is the Army's research branch, has a competition in June. And in that competition, you get to work with a simulated version of this robot. If you're in the top 6 of that competition, you get a Pet Man robot, which is the robot you're about to see. And then there's another competition a year and a half later with the Pet Man robots competing against each other. And if you win that, you get $2 million. So it's a big competition. It's a big deal. Let's take a look at what the robot looks like right now. This is about a half year ago, actually. Sure, in June when they release them, there'll be some upgrades. This is hard-coded to do certain motions just to show the capabilities of the robot. This is not a full Terminator yet. But this is pretty amazing. If you ever worked with robots and tried to program them to do something or build them, push-ups for fun. All right, so those are some examples of what robotics can do right now, and a lot of it, what we'll be looking at in this course is not how to build the robots, not how to build the mechanical, electrical contraptions, but how to come up with the algorithms that drive this, that are the software that drive the behavior of these robots. We initially touched upon logical representations of the world and so forth. It was a little bit of a bust at the end of the 70s, 80s period, but people are still working on it, and for some problems it is the right thing, and for some problems there are now probabilistic extensions of this that are being built. What we see in the slide here was one of the first examples of something that was a hypothesis of something that might be true, and nobody was able to prove it. The computer came up with the proof, and people said, wow, that's a correct proof, and it's actually a pretty nice proof. So this was Robin's conjecture. In this course, we'll look at constraint satisfaction problem solvers. Those are kind of the engine underneath doing this kind of proving through a computer. Game playing. One of the things that stood out in the late 90s is that IBM was building this amazing chess playing computer called Deep Blue. And it looks like that. So it's a rack, computer rack. It looks a lot like a fridge. It could do at the time, which is the late 90s, 200 million board positions per second. Evaluate them, compute some score for those positions, and based on that decide how desirable that position is. A very different way of reasoning about chess than humans do. At least we think so, that humans don't really think about 200 million board positions per second. Humans analyze what Deep Blue would do, and we'd understand almost all the decisions. We'd have a justification for it, yes. So there was something interesting going on there. Even though Deep Blue was thinking with a very different mechanism than the humans, it was acting rationally in the same way humans were acting rationally. They were just doing different commutations to get there. An open question right now is, how come Deep Blue has to look at so many configurations and humans think about so few? How do humans manage to somehow manage what they think about? So a meta computation. What should I be computing about such that I can efficiently compute things by considering very few things and then still get the right answer? In fact, that's something Nick is working on. Now, 96, first contest, world champion Kasparov against Deep Blue. Kasparov beat him. And he said afterwards, I could feel, I could even smell a new kind of intelligence across the table. Very nice of him to say that about the, essentially, IBM engineers who build it, right? Also sounds like something you can hang in your car, this kind of Deep Blue intelligence scent. Now, not too much later, Deep Blue beats Kasparov. In the interview after that match, what Kasparov said was, Deep Blue hasn't proven anything. Which probably says more about humans than it says about computers. Recently, there's been a lot of advances in Go. Go, at that time, used to be the thing that was completely out of reach of computers. Too difficult to solve, but there's been a lot of advances, and that's where people who work in game playing AI, a lot of them work in Go, and a lot of them also have started looking at things like StarCraft. All right. In general, a lot of what AI is about decision making. And without going into the details now, but we'll see a lot of details in later lectures, here are a couple of other examples. Scheduling, such as airline routing or military operations. Route planning, for example, in Google Maps, you'd ask for directions somewhere. Medical diagnosis. You might enter your symptoms and a computer would tell you what the most likely diagnoses are. Web search engines. You type something and it figures out what page it is out of these billion pages, many billions of pages, that you're really looking for. Spam classifiers. How does a computer sort through your mail to decide what's relevant to you and what's not? In fact, it does it so well now, and for most people, that you might not even remember what spam is because it rarely shows up anymore. Automated help desks, where you call in and computer at least tries to help you automatically. Fraud detection. Whenever you do a transaction with your Visa, MasterCard, and so forth, that gets sent back to a computer somewhere. That computer will make a decision on whether that looks fishy or not. If it does, then it might trigger a call to you to check that indeed you were trying to make that transaction. Product recommendations. You buy something on Amazon, often it'll tell you in the future then, oh, maybe now, since you bought this in the past, this is something you might want to buy now. And there's a lot more applications of AI that are being deployed right now. So what is the process here that we're going after? Somehow we're trying to design these rational agents. That's an agent. What is an agent? Well, think of it as this little robot, and it has some task, and someone needs to be clever about achieving the task. A little more formally, the agent consists of some sensors. That's kind of where it gets its input from. Then does some computation, on that input, and then output some actions. And then the environment around the agent will affect the outcome. The agent will get new percepts through its sensors, do a new computation, and then take a new action. And this loop will go around and around. So one example, you see the agent here. The agent is trying to pick an apple. The agent here could be the computer inside this little robot. The sensors feed into the computer. The computer then decides what the motor motions should be that actuate each of the legs and arms of the robot. And then the actuators actually make it happen. All right. So the goal is for this agent to maximize its expected utility. One of the hard parts, there's two hard parts to this question here. And we'll look at both in the next lectures. One hard part is somebody gives you an agent and an environment and what the percepts are and so forth. How do you compute the right actions? Another hard part is when you're faced with a real-world problem, how do you model that? How do you decide what the agent is, what the percepts are, what the possible actions are, how things can be actuated, and so forth. So there's a big modeling stage and there's a big solving once you've modeled the problem stage. So what you'll see is, as a general thread in the course, is that we'll have some standard format in which we model real-world problems. And that abstraction we'll then use to come up with solution algorithms for that abstraction. You'll then learn how, you'll then code up in the project and so forth your solution algorithms for these abstractions, and you'll also code up abstractions of problems that then can be fed into these algorithms. Kind of as a motivating example, let's look at the running example throughout this course, which is the Pac-Man game. Many of you might know this game. It's an old game, but it's still popular. The game here is about the yellow agent walks around in his maze. He's trying to eat these little dots. And there are these big dots. If it eats a big dot, then it becomes very powerful. It can eat the ghosts. When it's not recently eaten a big dot, then the ghost can eat the agent. So the goal here is for Pac-Man to eat all the dots. That means it wins. And if a ghost eats Pac-Man, well, that's the losing side of things. So let's take a look at what the AI techniques that we're going to look at in our implementation have been able to do for this kind of game. So here's a screen capture of running our code. So Pac-Man's moving around, and try to think about what kind of computation might go into making this happen. How would you program this kind of behavior? Whoa. Bold move, bold move. Okay, so what could go inside some system like this, right? The most naive thing would be to come up with a set of rules, right? You say, if I see a ghost within 2 steps to the right, move to the left. See, with a ghost, whatever the closest ghost is, move in the opposite direction. But when it's far enough away, try to eat the closest food, stuff like that. If you start doing that, you build something that's called a reflex agent. And you end up writing down a lot of rules, you get a very complicated behavior, and it's really hard to make sense of how to improve this. It's really hard to get to work. What we'll look at, kind of a different approach, and this is part 1 of the course, is how you make decisions by essentially simulating what would happen if you were to take a certain sequence of actions, and what might happen to the ghosts while you are doing your things, and then decide what sequence of actions will be the best thing to go with. So you first simulate many things, find out what the best scenario is for you, grab what you did there, and then execute it in the real world or in the real game. So we'll look at that in part 1 of the course. Part 2, we'll look at reasoning under uncertainty. So we'll see that often things are stochastic. And initially we'll have limited stochasticity, just some kind of dice that are being rolled, and that's enough. But in many real-world situations, there's stochasticity over many, many, many random variables. And we'll see how to deal with that. If there's hundreds or thousands of random variables that you want to deal with, how do you compute with that kind of uncertainty? That'll be part 2. And in that part, we'll also see how to do learning. So if you see something, some behavior, or you see some data, how do you learn from that, extract the patterns, and then generalize to a new situation? Throughout, we'll have applications the ones we highlighted already, some of them today. At the end, we'll have a couple of wrap-up lectures, and we really go in depth in more applications.